Hello, welcome to my talk on what are potential flows. In this talk, I will first introduce the difficulties in solving the four Navier-Stokes equation and their practical simplification to the problem, the potential flows. And then I will make the introduction on the assumptions in potential flows. Then we will see the definition of irrotational flow, as well as the physical illustrations of rotational and irrotational flows. And last, we will see where we can see the rotational and the irrotational flows. Generally, the analytic solutions for the Navier-Stokes equation are almost non-existent, unless for the very simple laminar flows. That's why the Navier-Stokes equation is listed as the one of the 7 Millenian problems. See the reference. To solve the Navier-Stokes equation, the 4 numerical solution is the direct numeric simulation, DNS. But this numeric simulation demands huge computer capacities, which are well beyond the current computer capacities. The popular research area includes the large eddy simulation, LES, and the hybrid lens LES models. But the computation is still beyond the current computer capacities for complicated flows. Today, the most practical numeric methods are the Reynolds averaged Navier-Stokes equation, LENS. But currently, we have significant difficulties in turbulence modeling for the complicated flows and the massive flow separations, etc. The most reliable way for solving the fluid dynamic problem would be the wind tunnel test and the flight test, but they are limited in their high cost and many other difficulties. For instance, the possible problem for scaling effect in wind tunnels, tanks, and for the flight test, the conditions might not be well controlled. However, in the earlier design stages, including the conceptual and the preliminary designs, faster turnaround time would be of vital importance, since we have many options and modifications in the optimization process. A very practical way to simplify the fluid dynamics is the potential flow theory. This is a very important and very useful method for solving the fluid dynamics, in which the flow is assumed to be irrotational. Therefore, we can reduce 3 independent velocity components to a single scalar potential function. Thus, to simplify the fluid dynamic equation to linear Laplace equation and Bernoulli equation. This method was extremely important before computers were available, before 1960s. And it is still very useful for solving some real practical problems of complicated structures with computers. To solve the real fluid dynamic problem, a very useful way is to simplify the dynamic equation by assuming the flow would follow some rules, such as the fluid is incompressible. The continuity equation is given as this, or the divergence of the fluid velocity vector is 0. Here, the Laplace operator is used. In fact, all the fluids are compressible. However, in many practical problems, when the fluid velocity is small, the fluid can be considered as incompressible. And we can see the divergence of velocity vector is calculated as this. Here, the Laplace operator is the gradient operator, and the velocity vector can be expressed as this. So, dot timing this together, we have the expression as this. So, this is the continuity equation. The advantages for this assumption is the fluid density is a constant. Therefore, it's a long parameter. We don't need to solve it. The usefulness for this assumption is when the fluid velocity is not very high. For instance, the Mach number is smaller than 0.3. So for the airflow, it would be less than 100 meters per second. That means we have many applications fall in the limit of the velocity, 100 meters per second. And then the fluid compressibility can be ignored. Thus, the fluid can be regarded as incompressible. Such a way can simplify the problem since the continuity equation can be expressed as a linear partial differential equation. The second assumption is that flow is inviscid flow. That means the fluid viscosity coefficient mu is taken as 0, or the kinematic viscosity coefficient nu given by mu divided by density, it is 0.2. Hence, for the Navier-Stokes equation, if the flow is inviscid, then this viscous terms would vanish because nu is 0 here. And the advantage of this assumption is the Navier-Stokes equation is degraded to Euler equation. And we can see the Euler equation is the first order partial differential equation. The usefulness of this assumption is the integral form of the Euler equation is the most used Bernoulli's equation in fluid engineering. This is for the steady flow. In fact, Euler himself derived the Bernoulli's equation in 1752. The most common fluids, water and air, both have very low viscosity. Thus, in many cases, they can be regarded as inviscid flows. So that's why the inviscid flow can be very useful because of the low viscosities for water and air. The third assumption for the potential flow is the most important and the fundamental assumption. The flow is irrotational. The mathematical equation is given as this. The core of the fluid velocity vector is 0. And if we express the core of the velocity vector, it would be given by this determinant. Here, the unit vector I, j, k are the unit vectors along x-axis, y-axis, and z-axis. And u, v, w are the velocity component. So if we calculate this determinant, it would be given the expression as this. Since for irrotation flow, the core of the velocity vector is 0. To make this vector to be 0, that means all three components must be 0. This component in the first bracket and the component this and the component this are all 0. So we have three partial differential equations given as this. So basically, a irrotation flow is a potential flow, since From the rotational flow, the assumption, we can define a velocity potential function phi here. So the velocity vector can be calculated as a gradient of the velocity potential function phi given as this. So we can see for this assumption, the advantage would be three velocity components are not independent anymore because the relation for these three equations. The three velocity components can be reduced to a single scalar function, the velocity potential function phi. That means we don't need to solve three velocity components, but a scalar function phi. Usefulness for the rotational flow can be the Pannar method based on potential flow theory have been well developed and applied. And the mathematics for the rotational flow is very strict and very beautiful if the flow is assumed as a rotational flow. We will see this in the following talks. And in this talk, we will talk more about the potential flow. As we have mentioned, a potential flow is an rotational flow. That is, the core of the flow velocity vector is 0, given as this. So this is the fourth equation for define what is a rotational flow. However, the physical meaning for such an expression is not very clear. To make the rotational flow more physically understandable, we considered the flow field and a closed circle C, so we can define the circulation of the flow around the closed curve C. The circulation is defined as minus integral on the closed surface C, given as this. And by using the Stokes theorem, this integration on a closed curve can be expressed as the surface integration, given as this. Here S is an arbitrary surface enclosed by the curve C. Since the core of the velocity vector is 0, therefore we can see for the rotational flow, the circulation on a closed curve would be 0. This is the second definition for the rotational flow, and this can be very useful. We will see in the talk later on. So we show a rotational flow means the circulation on a closed curve C is 0. In this slide, we will see how the flow can be distinguished as rotational flow and irrotational flow. For rotational flow, we can imagine the fluid element, the rectangle, rotate around its own axis when moving along the fluid path line. Since if we look at the circulation around the curve for the element, we can see the circulation would not be 0. Thus, the flow is rotational. For a rotational flow, the fluid element do not rotate around its own axis when moving along the path line. See this. And we can easily see the circulation around the rectangle would be 0. Thus, it is an irrotational flow. Based on the different definitions for irrotational flow, we have two different ways to check whether the flow is irrotational or not. The first method is to check whether the core of the velocity vector is 0. For every point in the field, calculate this. For instance, If we have a quiet flow, the simple flow, the solution of the velocity distribution would be given as u equaling to y divided by h times u0, the velocity, the up plate moving velocity. And v and w would be 0. And we can see the partial differentiation u with regard to y is given as this, and all other partial differentiation would be 0. So when we calculate the core of the velocity vector given as this, and the component as this, and this, so we can see this part would be 0 because w, v would be both 0. And this term would vanish because the partial differentiation with regard to z and with regard to x would be 0. And for the third term, this part would be 0 because v is 0. And we have only one term left in the expression. It would be calculated as this. So this is not 0. That means the core of the velocity for quiet flow is not 0. Therefore, the quiet flow is a rotational flow. The second method to check whether the flow is rotational or not is to make a closed curve in the fluid field and check whether the circulation is 0 or not, gamma equaling to this. If it is 0, the flow is rotational, and if the circulation is not 0, the flow is rotational. Again, we see the quiet flow, and the solution is given as this. Now we make a closed curve, a rectangle. We have 4 sides, 1, 2, 3, and 4. So when we calculate the circulation of the closed curve, we can calculate the integration for 4 sides, on side 1, side 2, side 3, and side 4. And we can see for side 2, the velocity and the dl are orthogonal, so this part would be 0, same as for the side 4. While for the side 1, dl and velocity would be same, so it is calculated as v1 times l1. And for side 3, the velocity and dl would be in opposite direction, so it would be calculated this, and the sign is changed from minus to plus. Consider the length L1 equaling to L3, so we have the expression for the circulation. It is given as minus V1 minus V3 times L1. For the quiet flow, we can see V1 would not be same as V3. So we can see the circulation around the rectangle is not 0. That means the flow is rotational. And we can also see some practical analog to the irrotational flow and the rotational flow. If we look at the famous Ferri's wheel, and we can see when the wheel is rotated, the carriage would always keep the right position regardless where the carriage would be. So the velocity on the carriage would be uniform as the velocity at the hinge, so here. And we can easily see the circulation on this carriage would be 0. And the same for this. Therefore, for the Ferri's wheel, it performs similar to irrotational flow. If we where the carriage on the wheel make a horrible rotating wheel. See this. When the wheel is rotating, the carriage would be in different position, especially when the carriage moved to the top of the wheel. It would be on a position of upside down. So if we make analysis to the velocity on the carriage, we can see the velocity on the carriage would not uniform. That means the carriage would rotate its own axis, and we can see its circulation would not be zero. This horrible rotating wheel is similar to the rotational flow. Now we have looked some other examples for rotational and irrotational flow. The first example is the laminar flow in an horizontal pipe. As it is well known, the laminar flow in a horizontal pipe, when the Reynolds number is smaller than 2300, the flow would be given, the velocity distribution would be given as this. The solution of the velocity u is given as this expression. So we can calculate the partial differentiation u with regard to y given as this. This is the only non-zero partial differentiation in this example. Now we can make a rectangular C in the fluid, and we can calculate the circulation along the curve C. As we have done before in the co-ed flow, we can see easily this would not be zero. And also we can easily find out the core of the velocity vector would not be zero. Hence, the laminar flow in the horizontal pipe is rotational. However, when the flow velocity is increased in the pipe, and the flow would become turbulent, especially when the Reynolds number is very large, say 10 million, the averaged velocity profile of the turbulent flow would be given as this. In the middle of the pipe, the flow would be very uniform, but near the pipe wall, there will be boundary layer. Now we can make a rectangle in the uniform flow in the middle of the pipe, C1, and we can easily find out the circulation along this curve would be zero for this uniform flow as the majority of the pipe flow. Therefore, the uniform flow in the middle of the pipe would be irrotational, even the flow is turbulent. And we can also make a rectangular curve in the boundary layer, C2, and this is very similar to the co-ed flow. We can easily find out the circulation on curve C2 is not zero. Therefore, the flow in the boundary layer is rotational. So this is the general case for the rotational and irrotational flow. In the boundary layer, the flows are always rotational, and far away from the boundary layer, the flow would be irrotational. The second example is the flow past the flat plate. The uniform flow past the flat plate, and we can see there will be a boundary layer. See this? And outside the boundary layer, the flow would be quite uniform. If we enlarge the velocity distribution, we can see the flow velocity distribution as this. And again, we can make a rectangle in the uniform flow far away from the boundary layer. And we can easily find the corresponding circulation, gamma 1, is 0. So the flow would be irrotational. And if we make a rectangle within the boundary layer C2, we can find the corresponding circulation around C2 would not be 0, very similar to the case in the co-ed flow. Thus, the flow within the boundary layer is rotational. So again, we see for the viscous flow near the boundary layer, the flow is rotational, and far away from the boundary layer, the flow would be irrotational.